Hello everyone. Now let's look at another important property which is called the invertibility. So our system is going to be referred to as an invertible system if the distinct input leads to a distinct output. So what does that mean? This basically means that for each input there is going to be a unique output, and it's not possible that for two different inputs the output is same. So essentially what we are saying is that a system is an invertible system if there is a one-to-one mapping present between the input and output, which essentially means that for each input there is a distinct and a unique output. And a system is going to be called a non-invertible system if there is a many-to-one mapping. Many-to-one mapping, which means it's possible that for two different inputs we are going to have a same output. Okay, so let's first take a few examples to get an idea of an invertible and a non-invertible system. Another thing which I need to mention before we jump to the examples is something which is mentioned over here. So if a system has an inverse system, so what essentially means is that if x of n is the input, it passes through the system, and y of n is the output, then if there is an inverse system and we give y of n the output to the inverse system, it's going to result back to the input. So if a system is an invertible system, cascading the system and inverse system in a series connection is going to give you back the original input which was essentially given to the first system, right? So that is one pictorial representation of a system having an inverse system. Okay, so let's have a look now at the few examples. Let's say the system equation is represented like this, which is y of t is equal to 2 times x of t. Okay, so now we can compute an inverse system. So at the moment, the expression is written, the output is expressed in terms of an input. So if I can express my input in terms of an output and it's a one-to-one mapping, then we say that we have an inverse system. So for example, if I want to find out inverse system x of t, that is going to be simply equal to 1 upon 2 y of t. So this particular expression is basically an expression of an inverse system, right? And this was the original system. So yes, this particular system is an example of invertible system. It has an unique one-to-one mapping, and that now here what we can say is x of t is the input and y of t is the output. This is the system equation. And if the y of t is given back to the inverse system, which expression is written over here, 1 by 2 times y of t, then what you are going to end up is getting back the input again, which was this one. So yes, this is an invertible system. Okay, let's take another example of an invertible system. Previously, we have looked at the expression of an accumulator system, and the expression was k goes from minus infinity to n x of k, right? And then we expressed this term before. For example, I can write this limit from minus infinity to n minus 1 x of k minus 1. Then I have taken the n term out, so there is going to be another term x of n over here, and then this particular term is simply y of n minus 1. If you derive from here, if you look at this one, this term is equal to y of n minus 1 plus x of n. So this is my accumulator system. Okay, so if you want to find out the inverse system, then the inverse system is going to be equal to x of n is going to be equal to y of n minus 1 minus y of n. So yes, I have represented my input in terms of the outputs now. So this is the inverse system and this is the forward system. And again, if I cascade my inverse system an original system in a series connection, just like in this particular visual representation, then what is going to happen? The input after cascading, I am going to receive the input back uh, after passing through the both systems. So this is the original system, this is an inverse system. So we are going to recover back the input. Okay, so let's take a look at now a few examples where you won't be able to get back to the input, where there is no more one-to-one unique mapping. So one of the example is, very simple example is y of n is equal to 0. So now essentially this is a system for which any input, irrespective of whatever the input is, the output is always going to be equal to 0. So what essentially we are saying is that for all the different values of the xn, for any value of x of n, x1n, x2n, x3n, for all the possible set values of the x of n, I'm going to get 0. So now this is a many to one mapping, right? So you can see all three inputs. I have just taken for an example three inputs. All these three inputs are basically mapped to 0. So there is no way that you can now predict from this point back to this that what's the value of 0, either it is x1n, x2n or x3n. So this is now a problem many to one mapping where you can't go back to the original input. So this is an example of a non-invertible system. Let's take a look at another example. The another example is y of t is equal to x square t. Okay, so when we try to write the inverse system is going to be equal to x of t under root y of t. But here is a glitch. There is going to be a sign of plus minus 1. So now again what we can see is that we are not sure whether it's going to be plus under root y of t or it's going to be minus under root of y of t. So this is the problem which we are now encountering. For example, we could have taken another example. Let's say that the input is basically plus 2, right? So then the output is the square of the input, which is going to be 4. And if I take minus 2 as an input, again, if I square up, it's going to give me 4. So what is happening is that two different inputs are being mapped to the same output. So now again, it's an example of many to one mapping. And the system over here mentioned is again an example of a non-invertible system. It doesn't have it as an inverse system. So now coming back to the physical realization, what do we mean? What do we infer? If we say that this particular system has an inverse, what do we mean by that? That basically means that from the output, we can recover back the input. Uh, if a system has an inverse system, if it's an invertible system. So why this is important? In communication, most of the time when we are sending a data from, this is just one example, when we are sending the data from one point to another point, we try to encode the data through some system. And then on the receiving side, we need to recover back the signal which we have sent. So essentially what we want is that the system which is encoding my data should be an invertible system, so I can actually recover back or decode the data when I receive it at the receiver side. So I can recover the input if a system has an inverse system or it's an invertible system, right? So any system which is non-invertible, we are going to use the word non-invertible, means that you cannot recover the input from the output when you receive it. So this is the distinction between an invertible and a non-invertible system. Thank you.